How you guys doing? I'm doing fine. Thank you for asking. So I'm going to do this problem right here. I was thinking about final exam questions for calculus-based physics, and this one came up. And the thing I really like about this problem, it's finding the change in potential due to this electric charge rod, because we can do it so many different ways. And there's even more ways than I can do it here. But I'm going to restrict motion perpendicular to the axis of this thing. And we want to find the change in potential. So let's just go ahead and get started. Let me turn off this camera so I can work full time, full force on the paper. So here I have a charge rod, and I want to find the change in potential going from point A to point B near that charge rod. Now, in a previous video, I derived the electric field, the magnitude electric field due to a charge rod, and I have this. So this says that if you're close to the rod, then the electric field is pointing away, radially away. You can also find this from Gauss's law, but it's the electric field is 1 over 4 pi epsilon naught, where that's a constant. 1 over 4 pi epsilon naught is 9 times 10 to the 9th Newton meters squared per coulomb squared. Times 2q, where q is the total charge on the rod, divided by the length of the rod and the distance away, which I'm going to call r. So I want to do this numerically also eventually, so I need some numbers that I'll use later. So it's a 1 meter long rod. I'm going from 1.2 centimeters to 1 centimeter away, and it has 20 Newton coulombs on there. So the first thing I can do is start with the definition of the change in electric potential. So we define electric potential. This comes from the definition of work, right? Because that's how we define electric potential energy. And the electric potential is just the electric potential energy, a lot of potentials in there, divided by the charge. So this is like the force dot the displacement. You got to integrate, and we have to integrate here because it's not a constant electric field. Okay, so let's just go and see how, let's just think first of all, I know I'm going to make a sign error here, I always do. Let's think about what should the sign of this change in potential be. So if I have a positive rod and the electric field gets smaller as it goes that way, and I'm moving this way, then it's like going uphill, right? So I should have a positive change in potential going from A to B. So let's just make sure that we have that. If I mess up, you can't hold it against me, okay? So I have my expression for the electric field, and in this case, I could call dl is in the r direction. So this delta v is going to be the negative of the integral. And now here, I know that I'm doing this wrong. From Ra to Rb of E, which is 1 over 4 pi epsilon naught, 2q over L, 1 over R dr. I'm still not deciding if that negative should be there, because I know the mistake I make is when you take E dot dl, okay, E dot dl but I'm going this way. So E and dl are in the opposite directions. No, yes, no, yes. So I think this should be plus. Oh gosh, I hate making a mistake, but it's all going to be good in the end. I'm going to figure it out. Okay. So now all this stuff is just a constant. I can pull that out, and I get 1 over 4 pi epsilon naught 2q over L. And we put the 2 and the 4, we don't cancel them because that's 9 times 10 to the 9th. It's just a dumb thing to do. The integral Ra to Rb of 1 over R dr. And now I can integrate this. If you need to look that up in an integral table, that's cool. I don't hold that against you. And I get 1 over 4 pi epsilon naught 2q over L times, and I'm going to write it out, the integral of this is natural log, so I get natural log of final Rb, so it's going to be ln of Rb minus ln of Ra, and you can't do that, right? I can't take the natural log of 1.2 centimeters. I can't even take the natural log of 0.0012 centimeters. I can't take the natural log of something with units. But if I have two natural logs subtracted, that's the same thing as dividing. So this is equal to delta V is equal to 1 over 4 pi epsilon naught 2q over L ln Rb divided by Ra. And that's that. Okay, now let's just switch over to Python real quick and check this, because I know I'm going to make a mistake and I don't even want to. I want to put in my numbers. So I'm going to put in RB equals 1.2, RA is A, and we're going to use these numbers anyway. So let's just switch over here to Python so that we can do this real quick, just to double check. It should be positive because I'm moving. The change of potential should be positive because I'm moving towards the thing. Okay, so let's just put all my values in here. I'll use them later anyway. Q was 20 nanocoulombs, 20. E negative 9. Km, I'm going to call 1 over 4 pi epsilon naught Km. It's like the magnetic K, right? I don't want to write 1 over 4 pi epsilon naught. And that's going to be equal to 9 times 10 to the 9th. L equals 1. RA equals 1.2. Oh, 1.2 times 10. 0.012. It would work either way because I'm dividing. RB equals 0.01. So now let's say dV equals, now I'm just going to type it in. Km, that's my 1 over 4 pi epsilon naught, times 2 times Q divided by L. Let's put this like that, even though it should be fine. All of that times the natural log. In Python, in this version of Python, log is natural log. So don't get that confused, of RB divided by RA, and let's print that out. Print, and it's dV because it's a change in potential, right? And that's going to be equal to dV, volts. And let's run that. And I get negative. See, I told you I did it wrong. Final minus initial. Let's just put the negative sign back in there. I know that's cheating. And then we get positive. Yes, if I'm going closer to the thing, I get positive. I know I fixed this problem before, and I'm going to link a video down below where I do this I make this mistake all the time, and you'd think I would learn from my mistake, but here I am. So I'll link a video down where I know I learned from my mistake so that you can know it and I can know it again because I forgot, but that's fine. So 65.6 volts. Okay, let's do this another way. Let's switch back to the paper. Okay, so there's another way that I can find the change in potential without using the electric field. Since the electric potential obeys superposition principle, I can say this. Here's my rod, and then here's my, here's V, this one's B. I'll call this VB, and this VA, and delta V equals the final VB minus VA. And these VA and VBs are the potentials with respect to infinity. And I can find that by assuming this rod is a bunch of tiny point masses. If I break this, let's call this the X direction for right now. And let's call this the Y direction. I break this into a tiny piece, I can find the potential at point B due to that tiny little piece, and then I can add up all the pieces and find the total potential without having to integrate over the electric field, instead integrating over the rod by assuming it's a bunch of point charges. Because remember, the electric potential due to a point charge, V, equals 1 over 4 pi epsilon naught Q over R. That's my potential for a point charge, and these are a bunch of point charges. So this is a point charge, has a charge dq. It has a location of y. And so what's the potential right there due to that point charge? Well, it's going to be dv. I'm just going to find the potential at this potential a distance x away. So dv equals 1 over 4 pi epsilon naught dq over r. But what's r? Let me change to a different color so we don't make a mistake. This is r. Right? So how do I find that distance? Well, if I know this is some distance x and that's some distance y, then r would be equal to the square root of x squared plus y squared. So I can put that in down here. Now what about dq? I can't integrate dq, but dq I can get in terms of dy. If the length of the whole thing is has a charge q and a length L, then the charge of this little piece is dq over its length dy. So dq is going to be equal to q over L dy. So I can put this in up there. So from that I get dv equals 1 over 4 pi epsilon naught dq, which is going to be q over L, dy, and all of that over the square root of x squared plus y squared. Now I want to integrate that and do. I'm not going to get natural log. I'm not. Okay, well, let's just see what I get. Okay, so if I want to integrate this, I'm going to have to integrate to get the total potential with respect to infinity. V is going to be equal to all of this stuff, which is a constant, 1 over 4 pi epsilon naught q over L. Integral, I'm going to add up these pieces from y equals negative L over 2 to L over 2 of dy over the square root of x squared plus y squared. And I'm not thinking right now how to integrate that. I was thinking about using U substitution. Oh, I actually think that would work. Because down here, I have, let's just look it up. Let me get my math table book. You thought you'd never use this. This is the 28th edition CRC standard math tables. Yes, you can look these up online too. Integrals, let's just see how you do this. See, so they have different forms here. So forms containing, I don't want a plus b times over the square root. I want forms containing, nope, now I'm back the other way. You have to flip through it, but you're looking through forms containing, because then it tells you, see, I don't want a plus, you can't even see that. I don't want a plus bx. Don't want that c cubed, what did it plus over a plus bx. Here's c plus or minus x. So I think it's going to be down here, a square root. I'm getting close. I can feel it. Okay, that's close. Look at that. Square root of a plus bx. I do not want that. Aha. Forms containing x plus or minus a squared. So my x is going to be actually y in this case. And it's going to be, I'm looking for x squared plus a squared 1 over. There it is right there. Okay. And there you see. There's my answer. So let's just write that down. So I'm going to write this is equal to all my constant stuff, 1 over 4 pi epsilon naught q over L. Now I have to evaluate the limits, so it's going to be, where did this go? X squared plus a squared is going to be equal to the log, which is natural log, of x plus the square root, oh, I'm sorry, which is y, plus the square root of y squared plus x squared. Yeah. Okay. So we did it. Now, and that's from negative L over 2 to L over 2. Did I? Yeah, okay. So now I'm just going to put in L over 2 for all these y's and negative L over 2 and divide them. This seems like it's not working out right, but I'll just do it the long way. 1 over 4 pi epsilon naught q over L. And this is the potential with respect to infinity. That's why. That's why. Okay. And so it does make it a little bit more difficult, because then I have to do this twice. I have to do it at x equals 1 centimeter and x equals 1.2 centimeters. Okay. So let's just write this out as the natural log of y. It's going to be L over 2. So it's going to be L over 2 plus the square root of L squared over 4 plus x squared. All of that, that's all natural logged. All of that over negative L over 2 minus negative L over 2 plus the square root of L squared over 4 plus x squared. So you can approximate this and get some answer, but I'm not gonna. I'm gonna put this into my calculator twice, into Python twice, and I'm gonna find the change of potential. Okay, it looks complicated, but there is an important point that I want to show you. Okay, so let's switch over to Python. Okay, so I already have my Q's and stuff like that in there. Let's go ahead and just define this as a function. Def, call it vrod, and I'm going to give it an x value, whatever x value that is. So I now need to just type in my equation. It's going to be, let's just call it temp equals km, I'm just looking at over here, times q divided by L. And yes, I am using global variables, and I'm a bad person for that. I get it. I know I'm a bad person. Times the natural log of, on the top, I'm going to have L over 2 plus square root L squared divided by 4. I think that's L squared divided by 4, not L to 1/2. I'm pretty sure it is. Plus x squared. All of that divided by negative L over 2 plus square root L squared divided by 4 plus x squared. I think that's good. And then I can return temp. So now that I made a function, I can just say VA equals vrod RA. VB equals vrod RB. And then DV is going, I'm going from A to B, is going to be VA minus VB, and print that. Print DV, I'm afraid this isn't going to work. And then I don't know what I'm going to do. DV volts. Here we go. I didn't even save it. Why is it negative? But it's the same thing. It's actually very good. Okay, let's see. I'm going to give you the code. Charge rod potential. Okay, I'm going to leave the negative sign alone because I'm confusing myself. I think maybe I was right in the first time. But then if you're going uphill, if you're going against the electric field, should be a positive change of potential. Maybe I got these RAs and RBs back. That's maybe what I did. I'm going to let it slide. Okay, it's a minus sign error. I know I'm a terrible person for not fixing it, but I will link a video down below that fixes it. Okay, now, but here's the thing, right? If this change of potential is from infinity to A and then infinity to B, and I take the difference, I get the same thing as I did it before, then shouldn't I be able to change point A to infinity and get the same as VA? So let's print out VA. So let's see which one is A. That's the one to start, right? So print VA, and this is the potential with respect to infinity, VA volts. Right, so that's the potential with respect to infinity. Now, what if I use this? Let me go back to the paper, because I'm going to show you it doesn't work. Okay, where was my other? Here's my previous calculation. If I want to find the potential at A, let's do B, it doesn't really matter. Then that would be, it'd be the same thing as taking this point A and moving it to infinity, and then I get the potential with respect to infinity. But if I do that, then as RA goes to infinity, I have the natural log of RB over RA. That blows up. That doesn't work. I can't do that. So why can I not do that? Why can I not do this and get the same potential? I'm letting you think about that for a second. And the answer is, are you ready? Okay. The answer is that this is only the electric field due to the charged rod when you're close to the charged rod. If you get an infinite distance away, this no longer works. And so I actually did derive this equation, the full version of that electric field due to a rod. The magnitude would actually be this. E equals 1 over 4 pi epsilon naught Q over R times the square root of R squared plus L over 2 quantity squared. That's the better equation. And what we did was we said, what if you are close to the rod and R is much smaller than L over 2, then this reduces to the one that we have. So let's use this and I'm not going to do it. You can integrate doing this, and I could look it up on the table, but instead I'm going to do a numerical integration just so I can make another minus sign error like I did before. Okay, so here's what we're going to do. Here's my rod, and here is my electric field, and it has some distance r away, and it has that magnitude. And so I'm going to start here at, let's say, r, not infinity, because I can't do infinity, right? I can't start from infinity and do a numerical calculation. I can start from something really big. Let's just pick r big equals, let's see, if that's 1 meter, big would be, I don't know, 5 meters. That's pretty big, and we can change that. And then I'm going to take the a step size. Let's pick a step size of, I'm going to pick something stupid small at first, dr, and call it delta r. Delta r is 0.001, so a tenth of a centimeter, which is probably too big. Let's do one more. 0.0001. And during that time, I'm going to assume the electric field is constant. So I'm going to start right here, assume the electric field's constant, and calculate the change in potential going over here. So delta V would be equal to E delta R. I'm assuming, I don't have to integrate, I'm assuming the electric field is constant. It's not constant, but I'm assuming it is. Okay. And so that would be with the change in potential, if I'm going this way, it would be positive, right? Because I have a positive electric field, I'm going in the opposite direction. Delta R is 0.0001. And then I can start right here and calculate the new electric field. So this is E1, this is E2, I can do it again, E3, and during each of those time intervals, during each of those space intervals, assume the electric field is constant. Add up the change in potential over all these points until I get here and see what I get. So the first thing I'm going to do is to print out, I'm going to do this at R, the closer one, RB. I'm going to do this all the way up to RB, and then I'm going to print RB. I can do RA. It doesn't matter. Let's just do RA. Okay, that's what I did before. So VA. So we're going to go all the way up to A. Okay, so let's switch back over to Python and let's do this. Okay, so I need to come over here, and I need to start with my values. So I'm going to say R big equals 5, and dr is 0.1231. Now I also need my my potential, my total potential. So let's call this VA2. It's the second way of doing it. And it's going to be 0, right? Because I'm assuming the starting potential is 0. I'm only calculating a change of potential. So I have to assume a 0 potential, and then I'm adding up all of my values as I go along. So I'm going to say while, I need R. Oh, let's see, let's just say R. R equals R big. Actually, I should just call that R. That's dumb. R equals R. That's just my starting value. And then I'm going to say while R is greater than RA. Do the following. Step 1, calculate the electric field. I guess I should define that too. That'd make it a little bit easier, right? Def E rod of R. And now I'm just going to type in the real equation. So it's going to be temp equals Km times Q divided by R times the square root of R squared plus L squared divided by 4. Return temp. That way I don't have to type that equation in, even though it's not a big deal. So now the first thing I'm going to do is I can go ahead and calculate the work, the change in potential. So I can say dV equals the electric field, which is E rod at R, times dr. And did I say that was positive? I did say it was positive. Okay. Now I'm going to say V equals VA2 equals VA2 plus dV. So I'm adding that little piece that I just calculated onto my total potential as I go up. Now I need to move R. So R equals R minus dV because I'm moving close, dr. I'm moving closer in. And I think that's it. So then I can say print calc VA equals, and this is going to be VA2 volts. Do you think this is going to work? I think it's going to work. Okay, let's see. Boom, boom, boom. It worked. Pretty excited. But still, why is dV negative? Let's see, let's print up here. Print VB equals VB volts. Just for fun. I just want to see. VB equals, oh, comma. So VB is greater. Oh yeah, because it's closer. Yeah, that's right. I got that backwards. That's where I got that backwards. It is going uphill. Okay. So you can try a whole bunch of stuff. You can make a graph. I'm not going to do that, but that can be your homework. You could try what if I start at just 2 meters away? What's going to happen then? It's still pretty good. Look, I get VA, the theoretical one's 1592 versus 1657. That's not so bad. Okay, and moving it up to 10 is crazy because I'm going to have a whole bunch of calculations that may even take a while. Oh, it didn't take too long. And then I get very close to the same thing. Okay, now one of the things too is as you get closer, the change in the electric field gets greater, so you could do something like changing the step size as you get closer to the rod to make a much more accurate calculation. You don't need to take small steps when you're far away because the electric field's not even changing anyway. You're super far away. But okay, so that's 2 ways to calculate the electric potential. Now let me just show you something for homework. So I want to make this video at some point, and let's just see if I do. What if I did this? One last thing for you to think about. Okay, so here is my rod. And here is VA with respect to infinity. Okay. And so what if I did this? What if I did the calculation, calculating the electric field, the change in EdV going this way? Because I had the expression for the electric field along the axis perpendicular to the rod. But what if I came in this way? Well, you can think of it over here at an infinite distance away, R infinity, V equals 0. And over here, R infinity, V equals 0. So electric field's conservative, the path doesn't matter. So if I want to, I actually could go all the way over here. That took no change in potential because they're both at 0, and then go down that way. So, but if I go this way, I should get the same thing, right? So if I start right here at some location and come in this way, I should get the same potential at A as I did coming this way. But how would you do that? That's a pretty tough calculation because right here, if I look at the electric field, it looks like this, it looks like this, it looks like this. It's not constant direction, it's not constant magnitude, so you'd have to actually do E dot dA, you'd have to do the dot product. And you'd have to calculate the electric field at these different locations, which is not trivial. But what if I did it numerically? What if I calculated the electric field of this numerically, which I did, at any location, and then you can do this. And I'm not going to do that right now. I want to do it later, but if you want to do that as a homework problem, that'd be super fun, and that's enough for me. I will talk to you later, and we'll do some more physics, and I don't have anything else to say, so I don't know, I'm still talking, but later.